Thank you everyone for being here today. I just want to confirm, can you see my slides? It's a picture of star trails and the observatory.
Yes, we can.
Perfect. Thank you so much. And I apologize again for the delay. I will be talking today about bringing the night sky to life, about how the Vera C Rubin Observatory will revolutionize the way that we explore the universe and understand its history on a very, very long time scale. So my name is Alysha. I'm the Deputy Nighttime Operations Manager for the Vera C Rubin Observatory, and I'll tell you a lot about this facility as I move forward. So the Vera C Rubin Observatory, which is pictured here with the full moon in all of its glory behind it, has completed construction and took the first photographs of the night sky in southern Chile just April of this year, April 15th. And it was a very, very important moment for all of us who have contributed to the project for many years now. So the Rubin Observatory shown here in front of the full moon is going to operate what's called the Legacy Survey of Space and Time, or LSST. What that means is this observatory, this large telescope contained in this building, will be scanning the sky for 10 years using the world's largest digital camera to create an ultra high definition time lapse of our universe. So the name Vera Rubin came from an American astronomer. It is the first observatory named after a woman. Vera Rubin who passed away in 2016. She was one of the prominent researchers and was one of the first astronomers who provided convincing evidence for the existence of dark matter. She was also a strong advocate for women in STEM and women in astronomy. So that's why this observatory has her name, is because this observatory will create some of the most detailed maps of dark matter and dark energy in our universe. So this observatory will essentially broadcast and create a very detailed map of the very thing that she discovered in collaboration with her colleagues. So the Rubin Observatory, where I am right now, I'm close to it. I'm not at the Rubin Observatory. Rubin is located in Chile, which is in South America, shown on this map here. Chile is a long, thin country on the west side of South America, and it borders the Pacific Ocean. So when you zoom in on the map, you can see the capital city of the country, Santiago, and about 5 hours driving to the north, there's a town called La Serena. This town is on the coast, it's on the beach. And then 2 hours inland from this town, up in the foothills of the Andes Mountains, we built the Vera C Rubin Observatory. The Vera C Rubin Observatory does have neighbors because Chile is a very, very special country. Because it's right on the coast, but also because of its long, thin border cutoff. On one side, it has the beach, the ocean, the Pacific Ocean, and in some cases, less than 50 kilometers inland, you reach the Andes Mountains. Very, very dry desert-like mountains in the top half of the country. And what this geological configuration offers is that the ocean brings in cool air, but right next to the desert, the air remains dry. So you get some of the best images of the night sky that possibly exist. The sky is very, very calm. There are not a lot of large settlements in these mountain areas. We do see lights from the city, but there are not a lot of city developments next to us, so it stays very, very dark at night. And that makes quality conditions for taking pictures of the night sky. The Rubin Observatory's next door neighbors, well, we have our auxiliary telescope, which is a calibration telescope. And then maybe a kilometer away, we have the Gemini South International Telescope and the SOAR telescope. And maybe 20 kilometers to the north, 10 kilometers to the north is Cerro Tololo, which is the oldest observatory in Chile, built in 1960. So I'm going to talk a little bit about science with the Rubin Observatory. From this view, you can see even better that how dry the area is. And when you look closely at this picture, you can see a layer of clouds looking to the northwest, where my mouse is hovering. So that might indicate to you that we are above the clouds, we're above the marine layer and all of that kind of wet, cool air that the ocean brings in, and we are able to see very clear vision of the night sky. So the Rubin mission, as you can see in this photo, is to capture the cosmos. In this video here, you can see this grid pattern being formed by our large wide field of view camera. So as you can see, we're going to scan the southern sky once every 3 to 5 days. Now, this survey will last for 10 years. So when we scan the sky, when we take the pictures of the same part of the sky, and we take a picture on night 1, for example, we can go back to that same part of the sky and take a picture on night 5. And what we can do with computer software is compare the difference between the two pictures and see what has changed over a matter of 2, 3, 4, or 5 days. What we can also do, as shown in this video, is as we create this large combined image of the sky, over time we will create these same large images of the entire sky, and we can stack them together, creating more and more depth. And as we are able to penetrate to fainter and fainter objects that we cannot see with the human eye, or that they're too far away or too dim to see. So like I said, Rubin will, when you take pictures of the same spot of the sky in 2 different times, we can compare the 2 images and see what has changed over time. We can, by doing this, detect new objects, detect objects that have changed with time, and detect objects that are in a different state of activity. So things that we can discover in this way are basically the appearances of asteroids and comets, of which there are billions and billions of these type of objects in our solar system. We can take pictures and detect pulsating stars or supernova. So when a star dies, when it spends all of its fuel on the inside, there is a massive event called a supernova explosion, when all of the material and gas it's produced over its lifetime collapses in on itself and then releases in a giant explosion of energy. And when we see these happen, we see them happen between one night and another, because there's always something happening in the universe. So all of these things we can discover just by taking pictures of the night sky, one night, and then 2 days later, that part of the night sky will have changed. So as I mentioned, we will be scanning the night sky every 3 nights for 10 years. And we will be what's called stacking those images with time. So whenever you see images or pictures of galaxies or of the universe or of structure, those images were created by taking many different individual pictures of the same spot and stacking them using computer software on top of each other. So you're basically combining the amount of light that's in each spot of that image. And you're able to reveal things that the human eye just can't reveal, because the human eye sees and perceives things very, very quickly. But when we're able to create time within the image, we can drill deeper and deeper into that place where we're taking a photograph. So the Rubin Observatory will be devoted to 4 principal science areas. There's a large group of astronomers and scientists who will be using its data to study the Milky Way and formation. Like I said, this telescope will also create the largest map of the universe that we will have, demonstrating where dark matter and dark energy could exist. We will be studying very deeply the solar system. And as I mentioned before, our solar system contains billions and billions of different comets, asteroids, and objects that are in orbit around the sun, but much, much further away than even our planet Neptune or Uranus. And of course, we will be looking at the changing sky. As I mentioned before, the universe and the night sky, things are always happening. The reason we don't know about them is because we do not have enough telescopes on Earth pointed at all different parts of the sky to understand all of the different things that are happening night by night. So that's at least on the southern half of the hemisphere where Rubin is built. We will be able to look at those same parts of the sky on a very short time scale. Other observatories can't do that. Other observatories may have to point to different parts of the sky for long periods of time. They may not observe the same object. After a few days, it may be months or sometimes even years before another observatory observes the same object. So we have a much faster telescope, and we have the ability to take pictures all over the sky very quickly. So we will be able to find all of these things that are happening that we didn't know about before. So over 10 years, it is predicted that the Rubin Observatory will detect 10 million changes per night in the southern sky. So if you can imagine, if you can look at this, this grid pattern that I'm outlining with my mouse is a representation of the size of the picture that we will take of the sky. So over 10 years, we will have 800 pictures of the same area of the sky that we will be able to stack and compare, so we can see all the things that have happened in just this one area. But imagine being able to do that for the entire southern sky. So as I mentioned before, there's a lot of things happening in our universe all the time. Stars are dying. There are high energy events near black holes. There are supernova. There are asteroids and comets passing. There's all sorts of things that are happening. And we will be able to see them as they are happening. This is an example of just a variable star or a pulsing star. A star pulses like that because of its energy and life stage, as it is expanding and contracting as it moves from one stage of its life to another. So we will also be looking at colliding stars, and when a star becomes brighter because it's being sucked into a black hole, We will be able to see events that have never been before seen in real time with the Rubin Observatory. Talking a bit about our own neighborhood and what we will see in the Milky Way. We will be, of course, the Milky Way band is beautifully visible from the southern hemisphere, especially during the summer months, January and February and March, kind of. So we will be creating the most detailed 3D map of the Milky Way, and we will probably see at least 1 billion or more stars in the Milky Way. We will also be able to map our stellar neighborhood, revealing billions and billions of more stars that were not either documented before or not studied in detail. So in this movie, we're showing how studying the Milky Way and small galaxies that are orbiting around it to understand how this group of galaxies came to exist and how it interacts with all of the galaxies around it. When we think about the scale, when we think about how big the Milky Way is, the human mind actually can't really understand how massive the Milky Way is. Most of us, we can't understand how big our solar system is. But what we will do with Rubin is not only look at the Milky Way and all of the galaxies around it, we'll look at the Milky Way and all of the other neighborhoods that are around it, being able to create an entire universal structure of what is thousands or even tens of thousands of galaxies. So getting into a bit of dark matter and dark energy. We may have heard these terms before, but very few or even no scientists really understand what dark matter or dark energy are. What we do know is that we can detect these things by its effects it has on objects or stellar or universe objects around it. So what that means is, for example, dark matter, what Vera Rubin discovered was that you have a very massive object in the center of a galaxy, and this means that everything rotating around it, because it's the most massive and because of the effects of gravity, everything rotated around it should have a very predictable orbit around it, just like our planets rotate around the sun and are gravitationally attracted to our sun. What she and others discovered was that all of these stars and all of these large objects inside a galaxy that were rotating around a black hole didn't follow the rotation curves as they were expected. Basically, what they found was that there was a presence of something of a lot more mass or a lot more stuff in that galaxy, causing stars and other large objects to rotate around this huge black hole in the middle in a different way than expected. So what they concluded is there is something very massive in that galaxy that we just cannot see. We can see the stars and the asteroids and the comets, and we can see all of the dust that is orbiting in that galaxy, but there was something else there, much more massive, that we couldn't see. And this is what became known as dark matter. So in this movie, you can see that matter bends the path of light and distortions and shapes or positions of the galaxies. These reveal where dark matter can be distributed, right? So it's basically this massive thing or this material that is having gravitational effects on things around it, but we cannot observe dark matter. We don't see it in any spectrum of light that we have available to us. So another thing is that we will be looking at as supernova. When a star basically shifts from one phase of its life to another, when it's spent all of its energy and converted all of its gases into other stages of gases, this creates a lot of buildup of energy, a lot of potential. And then it basically arrives to a point where all of this potential energy reaches an extreme limit and explodes outward to expel this energy of intense pressure and temperature. And for massive stars, this stage of life is called a supernova, when it explodes outward. Understanding the supernova, we can see by this huge, incredible increase of brightness of this star, we can use it to measure distance. We can measure distance from ourselves to that large emission of energy in that star. And what we can also do is we can understand how quickly that star is moving away from us. And what we know is that there's a lot of things like stars and galaxies that are moving away from us much faster than we calculated, much faster than we can explain with all of the material in the universe that's visible to us. So there's some unseen force pushing everything outward in the universe. And this is what has become known as dark energy. Again, when it's called dark matter, dark energy, that simply refers to the fact that we have not been able to confirm, or we have not been able to visualize the material, visualize the force that is creating this energy. But we know it's there by the effects it has on things around it. Another field of science that Rubin will be able to contribute a lot to is our solar system science. We will uncover millions of new objects. We will have an amazing capability to detect asteroids, and to detect asteroids that may be dangerous to people on Earth. And when we see these asteroids and we see how fast they're moving past our camera, past our observatory, we're able to calculate their orbit and understand if one day that orbit could potentially interact with the orbit of Earth. Other things we'll be able to understand is just why there are so many objects like that and how they became part of our solar system. So as I mentioned, all of these new asteroids and all of these new things that other observatories simply don't have time to go look at and study, we'll see such a big part of them passing over our observatory night after night. So we'll make thousands or tens of thousands of discoveries. And as we capture new objects, we'll be able to calculate their orbits, and we'll be able to determine if there are asteroids or orbiting objects that pose a threat to us, that are on a collision course with Earth. So as I mentioned, the Rubin Observatory began taking pictures of the night sky in April of this year. In that time, in just 10 hours of taking pictures, the Rubin Observatory has discovered almost 2,000 new asteroids that were completely unknown before. That's just in 10 hours of taking pictures. Now, if you imagine what that looks like in 10 years, there's a lot of potential new things that we will discover. And finally, one other interesting thing that Rubin will be contributing to, they're called, in the world of astronomy, targets of opportunity. So as I mentioned, there's a lot of things going on in our universe all the time. And the only reason we don't know about them is we simply don't have all of the facilities that we want looking at every part of the sky that we possibly can. Rubin will be looking at every part of the southern sky every 3 days. So this means that we will be able to see our changing universe on a much faster scale than any other observatory in the world. Targets of opportunity, however, are a part of a system what's called multi-messaging astronomy. So when there are other laboratories, other detection facilities that detect things like gravity waves, or that detect high energy neutrinos, we're able to detect these physical phenomenon in different facilities. We triangulate their positions where this force, where this effect is coming from in the universe. And then they send alerts to all astronomers, to all observatory facilities. Stop what you're doing, point to that part of the sky, and tell us what you see there. So Rubin is going to be also a part of that effort as a follow-up facility. So we will be working at night, and we will be taking pictures of the night sky, and we will receive an alert that says, alert everyone in the control room, stop what you're doing, point to this part of the sky and take pictures and tell us what you see. So that being said, just to summarize, Rubin will reveal new mysteries and lead to questions we haven't thought to ask. Every time we look at the universe in a new way, we make discoveries we could have never predicted, and now we will see more than ever before. I will take a little bit of time to talk about the facility and the camera. So the camera that we use to take pictures is the largest digital camera ever built. So it has 3,200 megapixels. Your camera may be on your phone, even if you have the best phone on the market, may have 32 megapixels or 3.2 megapixels. So if you imagine your camera and you multiply that by 1,000, that's what we're talking about when we're talking about this digital camera. Our telescope is a very fast telescope. That means it is short and has a short focal length. But what that also means is that it can move quickly. It can move from one place to the other very quickly without disturbing any of the mechanics or any of the optics that are a part of the telescope. And we also have a collaborative data management system. Because each picture has 3,200 megapixels, each image that we take is several tens of gigabytes large. That means that we are going to be taking a lot of data. So every night we will be taking about 20 terabytes of data. And these images will be transferred to storage facilities in the US, France, and the UK. You can see a close-up view of our camera, the LSSC camera. So if you need to picture it in a different way, think about putting together 40 ultra high definition television screens to look at one single image. The field of view of this camera, basically the amount of sky it could see, is about the same as if you were to take one full moon and duplicate it 45 times across the square of the field. And that's how big this field of view is. That's how big of the area of the sky that we can see with just one picture. The telescope is also unique in that it has two combined mirrors. What this means is that it makes it very quick for us to focus and gives us very stable focus. And it can move very quickly without disturbing the optics. So these two people in this photo are my colleagues. We are observing specialists. We are scientists that take the data, take the pictures every night throughout the whole night. So we take a new image about every 40 seconds. We will take 20 terabytes of data every night. And at the end of the survey, we will have 500 petabytes of data. And that's not something that we can even imagine. Our human brains, everything we ever learn throughout our life, everything we ever retain from memory and understand in one human brain is about 1 terabyte of data in a whole lifetime. So we're taking 20 terabytes of data every night. Because you can see on this global map, you can see the different paths that the data transfer will take so that all of the images will be stored in different places offsite. We have a data storage in La Serena, where is the town where I live. It will be linked to a site in Brazil and then transferred to the US data facility in California. Another data storage facility is in France, and the other data storage facility is in the UK. And these data points are basically showing you the path that the data will take to get to its final storage places. So all of these new things that we're going to discover and all of the things that we'll see night after night, we basically have software reviewing these images and producing alerts to other telescopes, to other astronomers, to other scientists to say, hey, there's a new supernova that we saw, or hey, there's a new asteroid that we saw. Here are its coordinates. Go take a look at what's going on over there. So Rubin will receive alerts from other types of laboratory facilities, but Rubin will also be publishing these alerts so other observatories can go look in that part of the sky and find out what's happening. So the software that contributes to these alerts, the data is processed within minutes to days. Software detects what has changed in the night sky and creates alerts and basically notifies other facilities of detected sky changes. There are different types of alerts for different scientific interests, such as asteroids or comets or supernova and things like that. And all of these different types of alerts, basically, classifying different types of objects. Scientists from all over the world have helped build this software so they can scan the pictures that we take and say, hey, there's a new object, or there's something happening with respect to our scientific interests in this picture. So we will take all the data collected over time, combine to create basically longer exposures and reveal fainter objects and extract the most info possible. So what's also special about this observatory is that the data we take is for everyone, everywhere, all over the world. It is a very important mission in this observatory to make the data accessible to everyone so that scientists from all over the world and in different places can participate and from different backgrounds. We also will have a lot of volunteers all over the world to contribute via Zooniverse citizen science. So what I want to share with you is that, we have a very strong education and public outreach department, and we have many resources available for free for formal education. So we have free online and classroom-ready materials for students. We have public outreach and mobile-friendly websites, visuals with videos and interactive activities. And anyone can participate in our citizen science projects, which are basically opportunities to contribute to the research on Zooniverse. So I want to leave everyone today with a quote from Vera C Rubin. And one of the important things that she said while she was alive was that she urged us, don't shoot for the stars because we already know what's there. Shoot for the space in between the stars because that's where the real mystery lies. So on these slides, you can see our website, rubinobservatory.org. We're on all types of social media, LinkedIn, YouTube, Instagram, Threads, and of course, X, Twitter, Facebook. And if you go to the rubinobservatory.org website, you can find all of those resources I listed on the previous page about the classroom-ready materials, about our mobile-friendly website and videos and interactive activities. And you can learn more about opportunities to participate in our citizen science program. Thank you so much for your time today, and I'm happy to take any questions if there's time to.
Wow. What a wonderful presentation. And thank you so much, Alysha. I was thinking here that the LSST camera has, you say 3,200 megapixels?
Yes.
And to think of it, my lousy iPhone 12 is only 12 megapixel. And you say that it's got 6 filters, right?
Yes.
And I realized that my iPhone 12 mini has got 10. So at least there's something better about it. That's on a lighter note, colleagues. Let's take questions and any comments. I find it quite amazing of the potential that actually this observatory actually has, particularly looking at the contributions that it could make in the upcoming years in terms of what lies there. It's quite scary that about probably more than 95% of the universe is still undiscovered. I find it quite scary, but yet, I guess, an exciting fact. Any questions, colleagues, or any comments? Please feel free. It is a safe space.
I believe Arjun
I
has
see
their hand
Arjun's
up.
hand is up.
Yeah.
Yes, Arjun, you can unmute your microphone. Did you unmute, Arjun?
Am I audible right
Oh, yeah.
now?
Yes, we can hear you.
Okay. So yeah, this is a very beautiful presentation, first of all, Alysha. And I had participated in the ZTF summer school that held before like 1 or 2 weeks in the last month. So there I understand about the Rubin Observatory working and about the ZTF data that, and I worked on some projects also. And right now I'm also working on some of the projects that on which I am going to apply the results of the Vera Rubin observatories. Okay. So I just have one question. That is, what are the primary computational challenges anticipated for the annual data releases? Like, are there concerns about systematic errors accumulating over like 10-year survey that might be difficult to trend or remove? So, yeah.
I'm not as knowledgeable about those processes, but the For example, like the alert brokers that I've talked about and the software that already exists, it is not stagnant, which means that it will change with time. We have tried to map out our data storage needs and our processing needs, but as you can imagine, based on what we find and based on all the different ways we need to process the data, these demands may change with time. But the scientists and software engineers who are contributing to the Rubin project are constantly thinking of new ways to confront those challenges. So even though now that we're taking pictures of the sky and we're testing the telescope and testing the images in all of these pipelines, we're already producing new improvements to our data management and to our data processing pipelines. Does that kind of answer your question?
Yeah. It's fine.
Okay.
Thank you for the question, Arjun, and thank you for the response, Alysha. Any more questions, colleagues? Or comments? Or compliments?